Read the extract below. So this is about brine shrimp. Now, people, this is an investigation, okay? And it being an investigation, you are going to get an investigation in either paper 1 or in paper 2 or in both papers. So I'm going to work through this very slowly because I want you to look at the process and the kind of questions you are going to get for an investigation and how to get full marks for that, okay? So, brine shrimp are small arthropods. They live in saltwater lakes. During favorable conditions, the female shrimps produce eggs and they hatch and you have little live young. Happy, happy days. So that's favorable. That's awesome. Okay? All things are good. However, when conditions are unfavorable, the shrimp produce cysts. Now, what is a cyst? Contains the embryo covered with a hard protective covering. That is what a cyst is, all right? In this state, the embryo stops growing and it can remain dormant for a long time. The embryos can remain dormant in this state for many years, and the cyst will only hatch when at the optimum salt concentration. Okay, so what they've done now is they've said to you, here are the shrimps, all right? And when things are good, they lay eggs, and the little eggs hatch, and you have little baby shrimp running around. Okay, but when conditions are not great, so that's the environmental conditions we spoke about, okay, for speciation, and artificial and natural, so this is natural selection happening here, okay? So when things aren't good, what do? They form this covering to protect their little embryos, okay? The embryo now becomes dormant. It's like a seed. You can take a seed and a seed will remain dormant until you put water on it and you plant it in the ground. Then it will start to germinate. Okay, the embryo can remain in this dormant state for many years, and there it is until things optimum, means things are perfect for it. Now, here the scientists wanted to investigate. Now, look at this. This is very important because this little sentence here gives you your dependent variable and your independent variable, and it gives you the aim of this investigation, all in this one little sentence over there. Okay, now look here. Scientists wanted to investigate what? The salt concentration, okay? So this becomes the focus of the experiment. And it is what the scientist decided on. Okay, they decide. Therefore, this is the focus of the experiment, the salt concentration. Therefore, this is your, this is your independent variable. Okay, salt concentration. That's your independent variable. Then resulted in the, and let's get another color here, resulted in the highest percentage of hatched cyst. And if it resulted, it tells you that this part here is going to be your dependent variable. Now, okay, look here. To find your dependent variable, think of the word draw me. Okay, the D is for your dependent or resulting variable that is observed or measured and plotted on the y-axis. because your independent variable, if you were going to plot your results, is always going to be on your x-axis. But just remember, DROMI, your dependent or resulting variable that is observed. In other words, you can look at it or you can measure it, and it's plotted on the y-axis. And if you remember that, you can never ever go wrong with what your dependent and your independent variables are. Independent, the scientist decides on it, and it is your focus of the experiment. Your dependent variable is the resulting variable. Okay, now, and now if I had to do an aim, what would the aim be for this here? Simply, scientists want to investigate, then you say investigation to determine which salt concentration resulted in the highest percentage of cysts. So all you are going to do, if you get asked to write the aim of this experiment, is to say investigation to determine and whatever the rest of the sentence is. How easy is that? Okay, now, what did they do? They did the following, okay? They prepared a salt solution with different concentrations. So you've got 0.5, 0.5, 1, 1.5, and 2. Okay? Who decided this? The scientists decided. They placed 30 mils of each solution in 1 of 5 beakers. Now, they all have the same, and the minute we see that we can add the word same, okay, same always talks to your validity of your experiment. It's always the validity. So how valid is it? We used the same species. We used the same temperature. We used the same conditions for all the different groups that we were going to test, which means you're reducing the other variables that can affect the impact of your experiment. So that was the same, so that's going to talk to validity. Took samples of the brine shrimp cysts using a dropper, okay, that's your tools. Counted the number of cysts in each example, sure. Recorded this as the initial number of cysts, which means this is all part of the how. How did we do it? Well, we took the sample and we counted the number of cysts in the sample, and then we recorded that number, and then we're going to do our experiment. Okay, we placed the samples into each of the 5 beakers. We left the beakers at room temperature, so it's the same. For 48 hours, that's also, they all had the same amount of time. Okay, recorded the number of cysts that hatched. Okay, and they calculated the percentage of cysts that hatched. So, is this a valid experiment? Definitely. They used the same amount of liquid or solution. They had the same room temperature and the same hours, and probably the same species of shrimp that they got the cysts from. Alrighty, so is it valid? Yes, it is. All right, now, in fact, while we're talking about validity, let's just look at reliability of a. So if they say, what is the validity? It's anything that you can add the word same to. When they talk about reliability, it's going to be repeating the investigation many times, okay? You can increase sample size and the number of samples, and you can also calculate the average. And all of that will then talk to the reliability. People, you must know this. Validity is wherever you can say the same thing was done to all the samples. Reliability, the more often you do the experiment, the more accurate your results are going to be. Because if your results are the same every time, it means that you've done everything correctly. All right, now, here we've got our salt concentration. So we've got 0, we've got 0.5, we've got a 1, we've got a 1.5, we've got a 2, okay? There are a number of cysts. Now you can see here, this one had 54, this one had 34, that one had 40, 40, 53. So we can't really look at the number of cysts that hatched, because if you start off with 54 and none hatch, if you start off with 34 and 2 hatch, or 40 and 6 hatch, it's going to be different. You can't compare this. Okay, so you calculate the percentage. And the minute you equate it to a percentage, you can then measure the different aspects. All right, so if we look at this, it says, state 2 planning steps to consider before collecting your samples. So what are you going to plan? So whenever we do planning, let's just put question 1 here. Whenever we do planning, we are going to look at when, where, and how. All of that is going to tell you what you are planning. So, first of all, where. We have to think about where we are going to, get shrimp cyst samples. Okay, because we have to make sure those samples are from the same place. All right. We have to also know where we are going to do the experiment or the investigation. Are we going to do it at home? Are we going to do it in a lab? Where are we going to do it? Okay. No, man, where? This should be when. This is when. Okay, so when are we going to do it? So if we think about it, when can we do it? Well, we can do, we have to, when to conduct the experiment or investigation. We also have to plan plus what equipment we require. Okay, and sometimes when you do an experiment, you have to get permission from authorities, from the Department of Water Affairs, whoever, to go and just take stuff and animals and plants from areas. Okay, so, but when? So when are we going to do it, and what equipment are we going to need? And then how? This how is very important, because the how is going to tell us, we'll have to decide on the concentrations of the salt solutions. Because remember, that's what we're testing. We are going to be testing here which salt concentrations resulted in the highest percentage of cysts hatching. So we have to decide, are they going to be, and well, clearly they already did, but so they decided on 0 salt concentration, 0.5, 1, 1.5, and 2. They decided on that. They could have decided on a whole number of different ones. They could have done 10 samples instead of only 5, 10 solutions out of 5, but they decided that. So they decided the concentration of the salt solutions. Okay, what else would you do? Oh, and also how to record the findings and data. Because that's important, and it doesn't help if you just say, okay, fine, well, we think that there were 120 that hatched. That doesn't work. You have to figure out how you're going to record it. So how you're going to check it, how you're going to count, and are you going to be accurate throughout? All right, so please, whenever you have to look at that, look at the where, the when, and the how you are going to do it. All righty, so So those are your planning steps. And people, you must know planning steps. Use your common sense. When, where, how. All right. Now, state the independent variable and the dependent variable. We've already done. The independent variable is your salt concentrations. Okay, and the dependent variable is going to be the percentage of cysts that hatched. Okay, you can also see it here. So apart from seeing the dependent and the independent variables here, here in this part, okay, you can also see it here with the data. That is your independent, and there are your dependent variables. Remember, your dependent or resulting variable, these were your results. Okay, calculate the value of x in the table and show all workings. Okay, let's do blue here. No, I need a... Okay, so what's that? Question 3. Okay. We're going to do the percentage hatched, okay, is going to equal, now let's just check x. X is here, so we've got 53 and only 1 hatched out of 53. So we want to know the percentage. So we say percentage hatched is going to be 1 over 53. 53 is your total, all right? And then we're going to times by 100. So where is my calculator? Okay, so we take 1 divided by 53 is equal to, times 100 is equal to, and no man, 1 divided by 53. Okay, so we take the percentage that hatched, all right, is going to be 1 over 53, which was the total, times 100. So 1 divided by 53 is equal to, times 100 is equal to, and then that is going to be 1,88679, blah, blah, blah. So you can then change this to 1.8%, or you can change it to 1.9 is probably closer. So let's make it 1.9%. So 1.9% or 1.88%. Either of those would have been correct. Okay, right. Then it says state 3 factors. So we're looking at 3 factors that were kept constant in order to ensure the validity of this experiment. Now remember, I said to you that for validity, you're looking for same. So what was the same? There was 30 moles of each, 30 moles of solution. There was the same room temperature and they were kept for the same amount of time. So question 4. Same temperature. Okay. Same volume of liquid, or you could have just said all samples had, what was it, 30 moles of solution. All right. Okay, so same temperature, same volume of liquid. I can't remember what the last, let's just have a look here. Oh, and for the same amount of time. So duration, so same amount of time in beakers. Or you could say that they were kept for 48 hours in beakers. Okay, so the same amount of time. And you can also, they can't mark it wrong, say the same species of brine shrimp cysts. So it came from the same species of brine shrimps. There you go.